So up to now we talked about thin film interference and the colors that we can create by putting a film on a surface. But another interesting application of thin films is trying to cancel light out, okay? And we use that usually on glasses and to make them a little less reflective. It's hard to stare at somebody when their glasses are reflecting all wavelengths of light. It can be blinding. And so often on glasses, and if you have a pair of glasses, you might notice that some of them have a tinting. Well, that's due to a thin film that they would put on them. And that tinting is there to reflect a lot of the visible wavelengths of light, or not to reflect, but to cancel that visible wavelengths of light that would be reflecting so that they would look non-reflective. People can see your eyes. They're cosmetically more appealing. Okay, so here you have a non-reflective coating and then just regular glass. These are just the regular glasses that are reflecting all wavelengths of light. So it appears that these lenses on top, you can see the person's eyes, but they are reflecting more of a blue-green color, and everything above 500, 600, 700 nanometer light is being canceled out. Okay, and that's what we'd have to look at. So let's take a look at a problem that you have in your text that says that, let's just draw it out. If I had a piece of glass, okay, this is my glass, and I coat the glass with a very thin film. Okay, this is my film. If I coat it with a film that has a refractive index of 1.38, and my glass has a refractive index of 1.5, okay, and then this is, of course, air at the top, so my light is coming from the air into the film and then coming out again. Okay, those would be those waves. This is where I'm going to have thin film interference occurring at that point. The question would ask, what would the thickness of this layer be? What would the thickness of that layer be such that, so T is unknown, such that it cancels 680 nanometer light. Okay, so we're looking at a problem where we're trying to figure out what thickness would that film be that has a refractive index of 1.38 to cancel 680 nanometer light. So if this was 680 nanometer light, which let's say is the most predominant wavelength that is in visible light, okay, we want to cancel it. We don't want to have any of that light coming out. So what we're looking for is destructive interference. So how would I be able to design an equation to look for destructive interference? And all the other problems we were looking for constructive interference. So I'm just going to expand this interface that I drew. Okay, let's make that film a little bit bigger. And let's make this glass a little bit bigger. Okay, so what we're looking at is that situation, and that would be 1 and 2. They're going to overlap. Okay, so what would that thickness need to be in here in order to cancel 680 nanometer light? So like the other problems, we have two equations. 2nt is equal to m lambda, and 2nt is equal to m plus 1/2 lambda. We need to pick the equation in this case. Instead of constructive interference, we need to pick the equation that would create destructive interference, that these two waves would come out of phase, half a wavelength out of phase. Okay, so first of all, I need to look at these boundaries. Okay, boundary over here and the boundary over there. And I need to see if a phase difference is occurring, or a phase shift, not phase difference. Okay, so n is equal to 1, n is equal to 1.38, n is equal to 1.5. So in this case, I'm going from low refractive index to high. So that means that I'm going to have a 1/2 wavelength shift over there. And then here again, I'm going from lower to higher, so that means that I'm also going to have a 1/2 wavelength shift. So both of these rays, when they come out, are going to be in phase with each other regardless, as long as I have a whole number of wavelengths in here. They're going to be in phase. So for constructive interference, I would have normally picked this equation. But in this case, we are looking for destructive interference. So if I selected this equation would allow this path to travel an extra half wavelength and then come out of phase. So this question is asking me to choose this equation for destructive interference. Now, recognize that I had to select, in this situation, depending on how it's aligned, I would select the equation to explain destructive interference. So now that I've selected the equation, the rest of the problem becomes pretty simple. So we're looking for the thickness. So thickness, oops, I'm going to change the color. Okay, so my thickness is equal to, and if it's the thinnest, m can be equal to 0. So it's going to be 1/2 times my wavelength divided by 2 times n. So my thickness, the minimum thickness, is going to be equal to 680 nanometer light divided by 4 times 1.38. Okay, now if we put that into our calculators, we should get the answer here. So 608, 4 times 1.38. Okay, would be 123 nanometers. Okay, and that would be the thickness that I would have to put of whatever that material is, that film with that refractive index. If I coat these with that specific thickness, I would block 680 nanometer light.